slides. We are on slide 27. Should look like this. It's the second dichlorocarbene slide. Yeah? Cool? Okay. Sorry, technology is difficult. I need to teach over here because there's a microphone. If I hang out over there, you can't hear me on the recordings. This is fine now. Okay. So, we're going to talk about what dichlorocarbene does. Because remember we talked yesterday about carbenes. Carbenes are an uncharged carbon with not enough valence electrons, right? It's got 6 valence electrons. But it's uncharged because, hold on, when is our break supposed to be?
8:50.
8:15?
8:45.
45? Okay. I legitimately, it doesn't even sound weird to me. I was like, all right, setting it for 8:15. Okay. 8:45. Just put repeat every day. Then I don't have to remember it. All right, cool. So carbon, when we're talking about like how many valence electrons an atom comes with, right? How many valence electrons does carbon start with? 4, right? Which is why we get to make 4 bonds usually because, well, it's got 4 half a bond. So carbene makes 2 bonds with hydrogen. Each of these come with their own valence electron, right? So now we've got 6 valence electrons around our carbon, and that's it. So these are unpaired electrons. They're not actually going to be just 1 electron by itself in this orbital and 1 electron by itself in this orbital, which is what unpaired sounds like it's going to be. But really, they're going to hang out together in an sp2 orbital. Yeah. With an empty p orbital, right? Because this is as far away as 3 things can possibly get. The empty p orbital doesn't really need to take up space or keep things away from it. So, or the empty orbital doesn't need to keep things away from it or take up space. So it just sort of ends up being, it goes to whatever it needs to be after everything else gets as far apart as possible, right? Vesper? So, carbene. Carbenes are synthetically useless. So you can make these guys and you can prove to yourself that you made them, and then they don't really react selectively or usefully. Let me make sure I have, sorry, let me plug this in actually just because you might as well have the slides going on for the recording. Okay. Cool. Hopefully somebody else to us. So, yesterday we started talking about dichlorocarbene. Dichlorocarbene is, if you go back 1 slide to where I told you to start from, we've got this guy, and we can do some weird resonance structures with this. And the reason we can do that, on the periodic table, the highest halogen, the furthest up halogen is what? Fluorine, right? I was thinking it was chlorine, and I was trying to come up with why we can do this. It's because it's fluorine, because once we get down to chlorine, we now have d orbitals energetically accessible, right? So it's not that fluorine doesn't have d orbitals, it's that the first d orbital is energetically after the next s and then p orbital. So fluorine is way far away from being able to use any of that. Chlorine, right after its p orbital, there's an energetically accessible array. Man, I need a periodic table to do those. Sorry, give me a second while I do ptable.com, which I have in my favorites. Okay, yeah, so chlorine has d orbitals energetically accessible. They're going to be right after the next s orbital, but they're there, they're close enough, we can get to them. So it's able to break the octet rule. So we can have some valence that looks like this. Let's keep it bent. We can have that, and we get a plus charge here, a nice charge here, and then we can go back the other way, put that back, and we can have resonance. So, more stable than the normal carbene, and in this case, more chemoselective than free methylene. So, we're going to do a mechanism real quick, where we prepare this by treating chloroform with potassium terbutoxide. Add some 2 slides. Sorry, I keep skipping the product of what this actually makes, because that's cool. What does it do? So it's not positively charged, but it does count as an electrophile, and these guys like to react with nucleophiles, specifically double bonds. So if we've got CO2C, and the mechanism for this is super easy. I mean, really complicated. Get ready. You might miss it. All right, it makes a triangle. Cyclopropane, yep. And in this case, since we've got a ring, remember we talked about yesterday when we put the ring, okay, it's a 6-membered ring, so actually it's gonna be like boat or chair, but you know, if we really, even though it's boat or chair, there's still kind of a general, these guys are up and these guys are down, right? Even if some of them are axial and some of them are equatorial. You guys remember axial equatorial with cyclohexanes? Okay, so even though some of them are going to be axial, some are going to be equatorial, like you still have the axial that point up, those are above the ring, right? And the equatorial that point to the side, well, the ones that have an axial that point down, these equatorials are the up ones, right? If you've got this going on that carbon, this is the up. If you've got this, then this is the up. So In this case, whether they're both up or both down, they both do the same thing when we react with a ring. And this is called sin. So, like, cis is to trans, such sin is to anti. That is not the shape I was trying to draw. That's a ring. Yeah. Both down. So, we get that selectivity. What if we what if we react to dichlorocarbene with a double bond that's not in a ring? So, on your slides, we use, oh, that's too high. So in your slides, we've got that, and we have this. We could just draw the products in this case and not do mechanisms, but like the mechanism is so easy that honestly, when dealing with these, I always draw the mechanism if I'm trying to predict products. Like if the mechanism is easy enough to do, then I usually draw that, or at least part of it, when trying to predict products, just because it gets you into the point where you start going, okay, where do I have electrons, where do I not have electrons, and where should things go, right? So if you get to the point where you're trying to predict reactants, or predict products, and once we get to next chapter in, hopefully before the break, after the break probably, there'll be a lot of things that look similar because we'll always have a carbonyl and then we'll do something with it. You're gonna do the same thing. You're gonna identify what has lots of electrons, could be a nucleophile, what has not enough electrons, could be an electrophile, and try to draw arrows like that. So, you don't always have to draw your arrows for this if I don't ask for the mechanism. I just think it's easier because they're easy and they show exactly what happens. So, our product for this. That, right? There. Yeah. Yes.
So you keep the double bond.
Good call. Okay, so now, why am I talking about what kind of stereoselectivity we retain or anything? Because this isn't a ring. But each of these is now a stereocenter, right? Yeah, one. Yeah, there's 1, 2, 3 different things and a hydrogen. So each of those is a stereocenter. So we do still need to talk about what kind of stereochemistry gets retained or gets changed here. Because, all right, how do they draw this? They just draw that, and then they do a nice big Is that conveying what I wanted to convey? A nice little triangle coming out of the board with stuff going behind it. Oh, and then there we go. Okay, so at the very beginning, we had this going on. So basically, we make sure that in the end, we keep that going on. The hydrogens both go down, this both goes up, this comes straight out of the board, and then has a chlorine up and chlorine down. Yeah? So we don't retain a double bond, but we retain stereochemistry from that double bond. Yeah? If we had trans here, then our final product would be exactly the same, except it would look like this. And yes, that would be really, it wouldn't be too annoying to figure out how to draw that without trying to do the triangle coming at you. I guess you could just sort of do a triangle. You don't have to draw stereochemistry on these because, like, they're the same. And then, as long as you have wedge bonds are difficult when I have to do carbon CH3. Okay, that's CH2. I'm going to draw it like that because I don't know how to draw a line straight from a wedge. I might be able to, but I don't know if it would look right. Dot, dot, H. And then if we're doing this one, we would just make sure that that one's our H. Nah. Yeah, that's how I draw that.
So what's the difference if it's cis or trans?
So if it's trans, you end up with this. And this. If it's cis, you end up with that. And it looks like it doesn't super matter, except we've got okay, so usually we draw it where like one of them is toward like going into the board directly, and then we try and make that the hydrogen, right? In this case, the way that this is drawn, I don't exactly have one thing going into the board, but I do have one thing coming out of the board. Part of the reason I have it drawn like that is because, well, we've got a ring, and so really all three of these, let me color code, all three of these bonds are going into the board a little bit, like a nice little tripod back there, and then the one bond's coming out like this. So, that being said, if you were to try to put the hydrogen behind it, you would have if that went back, you would have a carbon with that. That's the ring. I'm not drawing it. And that's the other part of the ring that has the chlorine. There we go, that's a ring. So then we would number them. I want to say a ring has higher priority than this, especially because it's got this on there eventually. So I think we would number 1, 2, 3 with the hydrogen in the back that goes this way, which is like we're turning a car right. So that has R. That's an R. What has R configuration? Is that how you say that? It is R. It is an R stereocenter. Yeah? Okay. So, cis, trans. Is that easy enough to tell the difference? Yes? Okay. Example 15.5. So the examples in your slides, you will have the answers to those examples in your post-lecture slides. So I highly suggest you go over them at some point and practice them, especially if we haven't done them in class. And if you have questions, you can, if you have questions that you would want to email, I wanted to specify something real quick. For ways to get help in this class, if you're trying to email me a content question, put it on the discussion boards. But you don't have to go to the discussion boards instead of talking to me or instead of talking to our TAs, right? So first line of defense, come bother me before class, during break, after class, come to my office hours, come to my TA's office hours, bother your TAs in recitation, or email me if you want to just set up office hours outside of when I normally have them. Also, we have an official Learning Commons tutor for this class. So you guys can make online appointments with the Learning Commons, with our tutor at the Learning Commons. If you do, this is kind of hard to see, but if you search UC Learning Commons, you can get to a website that kind of looks like this. And up in this, right under Learning Commons, it's got a bunch of options. One of them is schedule a service. So if you click that, it takes you to a different looking website. It kind of looks like this for me. I don't know what it looks like for you because when I click students, it doesn't give me the, here's what it looks like if you're a student. It just gives me a list of you guys. So I'm pretty sure over here in your courses, I assume you'll have something like this and you can click on it. But we have a dedicated tutor for this class, for this section of this class. So you guys can make online tutoring appointments with him, and that is also a resource at your disposal. Just so you guys are aware of the ways to get help. And he has access to our, I'm pretty sure I added him as a TA to our Canvas class. I think I did that a while ago, but I'm gonna double check tonight and make sure that I added him. So he should have access to all of the stuff that you do and potentially things that you don't, although your TAs have access to all the things that you don't have access to yet because I just shared my OneDrive folder with them. Usually I don't put stuff on Canvas and like not publish it. I just put stuff on Canvas when I'm ready for you guys to see it. So your tutor may not have access to additional things, but they've got access to the answers guide, the answers manual for your textbook too. So that's at least enough to get through these examples and such. Let's see if this has changed its mind. Okay. It was worth a shot. All right. So now let's talk about Simmons-Smith reactions. Is that still? Okay, yeah, that's still connected to the thing. Simmons-Smith is the answer to, well, what if I want to do exactly what you just showed me, what dichlorocarbene can do, but I don't want those chlorines on at the end. I just want hydrogens there. How do I do that? Because methylene, is that how we named the simplest carbene? Methylene, yeah, methylene is the simplest carbene. It just sounds wrong to me. Methylene is synthetically useless, right? So how do I do what you just showed me, but I want those to be hydrogens? And right before we get there, sorry, I interrupt my own thoughts with other thoughts, but feel free to stop me and just let me know if my interrupting thoughts with other thoughts doesn't work at some point, and you're like, back up, just say both of the things that you were gonna say separately because it didn't work, right? That's the deal. The deal is I do my best and you guys agree to interrupt me with questions if necessary. Yeah? Okay. Just reminding us of the deal, because a lot of instructors don't like that, but like, I need it. So we talked about dichlorocarbene. You can do that with bromine. So you can have dibromocarbene. The example that was after this used bromine. I think you could probably use diiodocarbene. I can't think of a reason why you wouldn't be able to, but I feel like you might not do that anyway, just because, I don't know, usually iodine, compounds with iodine are more expensive than compounds with bromine and chlorine. At least like organic compounds that have like an iodine or a bromine or something substituted off of them. Iodine is always more expensive than bromine, sometimes to the point where like half a gram of this with the iodine off of it is like $350, $400, which isn't a big deal when you are at an R1 university and you're with an advisor who has NSF grants, and she's like, yeah, whatever, get it from Sigma. But it is a big deal when you start a master's at a program that does not have a whole lot of NSF grants, and the graduate college gives you $500 to do your master's, and the chemistry department goes, here's $500 more. You have $1,000 for your chemicals. This will be fine. Some of you do organic synthesis. Hope your reactions don't fail too many times. Ask me how I know. So, iodine containing compounds are usually like way more expensive. Sorry, I gave like half a gram for like $350. For one of the compounds that was about the case, the bromine containing compound, I couldn't find it in less than a 25-gram bottle, and it was, I don't even remember how cheap. It was 2 digits. The price was 2 digits, and not an alarming 2 digits. It might have been like $16. Because if it's in the like 50s or 60s, usually they'll give you an option to buy like less of it. But I want to say it was like 25 grams for like $16. So they just, if you want to buy this, you have to buy 25 grams, at least from us. So, yeah. Probably not going to do that with iodo, but I think it'll work. Okay. Simmons-Smith reaction. We're going to try and make a triangle where we don't have chlorines on the end, right? So, first, we have, and this is on, give a slide for this guy. It's the first slide labeled Simmons-Smith reaction. I should have put, oh, that doesn't work. I should have put slide numbers on all these slide decks before I started messing with them, and then change the slide numbers so that they never updated with how many slides there were. That way, I have different numbers of slides than you do, because like, I didn't just leave blank slides in when mechanisms took multiple pages or something, or like, for the answer to a thing, but it's hard to keep track of what slide we're on. So, Simmons-Smith, we've got we're going to start with this, CH2I2. That is diiodomethane. We are going to add have that in a they call this a zinc copper couple. Don't ask me what that is in real life, because, man, I don't know. Those are metals. I use metals to make other chemistry happen with the like 5 elements or so that, we all know actually exist, rather than all those other elements that nobody cares about. Carbon, oxygen, nitrogen, hydrogen, I guess some of the, then throw in some of the halogens. That's all I care about. But that's a zinc-copper couple. Okay, we're gonna add those together in ether, and we are going to get ICH2 ZNI. Iodo, methyl, zinc oxide, also known as the Simmons-Smith reagent. So we're gonna get that, and this is an example of a carbenoid. So carbene, right, has 6 valence electrons and acts as an electrophile. This is a carbenoid. So basically, it's a thing that acts like a carbene, but you never actually end up with a carbon without a full valence shell around it. It just does the same things that those tend to do. Okay. Oh, they have a nice little definition for us. Compound that delivers the elements of a carbene without actually producing a free carbene. Yeah, that's what I said. All right, so on the next Simmons-Smith reaction slide, we've got some examples. Let me make sure I'm not skipping things from what I wanted to show you here. Nope. That's after this. Cool. Okay. So this it gives an example with 5-membered ring because it hates me deep down inside. 2I2. And then, gosh, I wish I could see. NCU, ether, and instead of drawing that out, they give us this. We do a 5-membered ring, and then now a lot of the times we had we would have a ring. Last time we did, angles are hard to draw. We had something coming out of it like this, right? We had that because we had the bond inside the ring. So this time, it looks different because this guy is next to the ring, so we get this. And then our byproducts, zinc, I2. Don't ask me how they get to the name. Is that 4.2? Spiro 4.2 heptane. That's definitely not a comma. And this, stuff like this, is why IUPAC is really cool at first when you learn it, especially because right after this you take biochemistry and they name things after who discovered them, and then when they have a 1, 2, 3, and 4, they're not actually used in a process in that order. They're named in the order that they were discovered, which means 4 is probably used first, and 1 is actually not even used in this metabolomic cycle, it's used over there. And organic chemistry, IUPAC, seems really nice with the naming until you get to a certain point, and then you stop doing that and you start using SciFinder. which, by the way, for future reference, SciFinder or SciFinder N, we have access to it on campus. You're going to have to go through the library the first time you use it, or I think you can just go straight to Reaxys, and if you're on campus, it'll work. I'm pretty sure you can just go straight to the Reaxys website, and if you're on campus, it'll work. Otherwise, use the VPN, and I still don't think you have to log in, but if you log in, it lets you save things. SciFinder N, you're going to have to make a login. The first time you use it, you're gonna have to go through the library, and if you just go to the library's website, UC Library's website, and you search SciFinder N, it'll bring you to these like research guide things. It'll bring you to a research guide, like kind of a mini website inside the library website that's all about SciFinder N, and I made that. That's how I know it's there. So it's got instructions for the very first time you log in and then all the other times. And it should have, yeah, I'm pretty sure still has some of my old workshops from when we were switching over to SciFinder N from SciFinder. Anyway, naming is really nice until it gets to a certain point, and then you can go to these and you can just draw your compound and search it. So, that's the thing. If you're ever looking to make something later in your life, like plan a synthesis, you can use these. In fact, both of these have a retrosynthesis planner, so you can draw out the molecule you want and then say, hey, how would you synthesize this if you were going to computer? And it goes through, it takes reactions that have definitely been done before and published in literature, and it tries to make it using those. And if it can't, then it starts looking into reactions that have been done in literature that are similar to something that could be done maybe to make your thing. It's really cool. So you can look up spectra. Reaxys is better for spectra and physical data. SciFinder N is better for literature searches. So now you know. And in case you find literature searches where there are papers that you don't exactly have access to, or at least not access to right now, I do not recommend that you go to Sci-Hub or LibGen, Library Genesis. I do not recommend that you go to either of these things and use the DOI, which is just like, it's usually .org/ some numbers / like, I think for, it's like JOC dot some more numbers or something like this. These are just like some numbers and then a slash and some other numbers. Sometimes there's letters in there. That DOI is the address to any research paper. Like you can search for the title of the research paper, but then it's searching for, like, sometimes that works, sometimes it doesn't. The DOI, that's always the address of it. So if you type in doi.org/ paste the DOI in there, it may not take you to a place where you have access to the paper, but it will take you to the publisher's website for the paper. If you need access to them, I do not suggest you go to the pirating site Sci-Hub or LibGen, because those are pirating sites and that's illegal. These are illegal ways to access research papers. LibGen is an illegal way to access textbooks as well, using the ISBN, which is kind of like a DOI but for books. So I do not recommend, I recommend you stay away from these two websites that you could use for pirating. that enough disclaimers? That I was both helpful and also hopefully won't get sued?
Yeah.
Okay. I'm not actually sure if like the university can get sued because they gave me zero training for lecturing and like I'm allowed to lecture or not, or if I could personally get sued because who knows. But I do not recommend you go to either of those things because pirating is wrong, especially since when you pay a whole lot to read a research article, the authors of said research article get no money. It all goes to the publisher, and the authors of that paper already paid the publisher to publish their paper, too. So everybody thanks them. All right. I remember now why we got so behind in lecture schedule. It's gonna be fine. We've still got our exam, not this coming Monday, but the Monday after, and we'll cut out a chapter if we need to. Okay, have a break. Have a